Hey folks, how are you? My name is Ray Arvidson. I'm a professor at Washington University in St. Louis. I'm a planetary scientist. I'm also a Viking resident astronomer. Hopefully I've seen some of you on the Orion and Jupiter. And occasionally I'm an enrichment lecturer for geology and environmental sciences on some of the other ships to Iceland and other places. We're going to talk about Mars today. And what I'm going to try to convince you is back in the day, billions of years ago, Mars was warm and wet, and the rocks we're going to look at show that there were rivers and lakes. There were organic materials in the lake beds. So the whole idea of Mars once being a little bit Earth-like, not completely, and maybe having life is not absurd. And that's the reason that Mars is right now a topic for exploration, a target for exploration by a series of spacecraft on the way. So if we go to the next slide, please. Where are we in the solar system? They're the inner planets, Mercury, Venus, Earth, and Mars. And I study Venus, I study Earth, I study Mars. Earth is my favorite planet. Mars is my second favorite planet. Venus is also interesting. Earth is in the habitable zone, and the temperature on average about 59 Fahrenheit. And it just is right in terms of having liquid water, which is necessary for life, as you know. Venus, on the other hand, is hotter than you can make your oven at home. The mean annual temperature is 864 degrees Fahrenheit. It's not a vacation spot on the surface. It's a runaway greenhouse gas effect in terms of a very dense CO2 atmosphere, as we'll see in a minute. Mars today, extremely cold. On average, minus 63 degrees Fahrenheit. Occasionally gets up to 32 Fahrenheit, but not often. So you're not going to have liquid water today. But in the past, hopefully after this discussion and lecture, we'll convince you that in the past, the rock record says that this planet was warm and wet and was probably habitable, may have had life, we're not sure. That's the reason that there's so much excitement about exploring our red planet. Also, if you go outside tonight, just after sunset, and if you're in the northern hemisphere, Mars is going to be that little red dot very close to the eastern side of whatever you're looking at. And in the morning, if you go out there just before dawn, it will be off to the right-hand side or the western side of the sky. And that's because it's in opposition. And opposition means that Mars is exactly as shown on my diagram. It's on the other side of the Earth relative to the sun. And in fact, it's one of the closest approaches let's see, what's the number? 39 million miles away on October 13th. And that's why you can see it as kind of this red dot in the sky, either just after sunset on the east or just before sunrise on the west. But let's take a look at these various objects, Earth, Venus, and then really focus on Mars. Next, please. Here we are. Earth is just right. Of course, it's getting warmer pretty quickly because we're pumping in CO2 and other greenhouse gases at a really fast rate due largely to fossil fuel burning. But it's a place we like. It's a place we live. The moon, there's no life there. There's no atmosphere to speak of. Iceland shows that, we have liquid water, we have water vapor in the atmosphere, and we have ice. And that is basically the Goldilocks or the habitable zone, where liquid water exists over an extended period. In fact, a view of the Earth shows that it's water Earth. Over 70% of the surface is covered by water. So it's not surprising that our bodies have an enormous amount of water, and we're dependent on water to have life and to live in a healthy way. You don't want to get dehydrated, for example. And next slide, please. Oh gosh. Here's our sister planet, Venus, 94% of the Earth's size, but 864 degrees Fahrenheit on the surface. It rotates once every 243 days. It has no magnetic field. It rains sulfuric acid at the top of the atmosphere. Those are those white clouds that you're looking at. By the time you get to the bottom of the atmosphere, that is the surface, that sulfuric acid has evaporated. But the massive amount of carbon dioxide, 90 times the amount in the Earth's atmosphere in your room, means that the sunlight gets in, it heats scattered, some of it heats up the surface, but those gases, the CO2, just absorbs a lot of heat trying to get out, and it pumps up the temperature to an enormous greenhouse gas, a runaway greenhouse gas producing 864 degrees Fahrenheit. Gosh, it's not a place I'd look for life, although there's a recent discovery from multiple telescopes of phosphine in the upper atmosphere. And phosphine is found in sewage piles on the Earth, and if you bake those sewage piles, it goes away. So some people think that phosphine, which is phosphorus with 3 hydrogens stuck to it, may be a biological gas, but we don't really know. So there was a lot of excitement recently when that article was published that phosphine may indicate life in the upper atmosphere or may not. So we can come back to that in questions and answers if you folks wish. So not really a habitable place in my opinion, certainly not at the surface. Next. We had a mission back in the late 1980s, early 90s that I was part of called Magellan. And the atmosphere is so dense and the sulfuric acid clouds are so opaque, you can't see the surface with your eyes. So we flew a mission called Magellan, and it actually penetrated with radar, long wavelength radiation through the atmosphere and bounced off the surface so we could make images of the surface that are basically radar images. Next. And we mapped the whole surface. We only had one band. We didn't have color, but you know, color is kind of nice to look at. So this is just colored red, so it looks nice. You see that little white splotch kind of in the upper middle? That's Maxwell Montes, which is a huge mountain. We did experiments with this radar system of bouncing the radar beam off of Venus and then listening in the Mojave Desert in California with the Goldstone radar antenna. And what we found is that the only possibility for explaining the strength and nature of that scattered radar from the surface is the mountains of Venus, including Maxwell Montes and the other bright areas, are actually covered with metal snow, like iron sulfides and other really weird metal species evaporate or sublimate, go from solid to vapor form from the plains of Venus and then snow out or produce frost up on the mountains. So it doesn't have a hydrologic cycle as we know on Earth. It has kind of a metal cycle. So it's not a place to go to search for life, at least on the surface. Next. This is just a perspective view that we made from the orbital data. And you can see Sapis Mons, which is a volcano, and it's really bright at the top. And again, might be covered by this weird metallic snow. And you can see some other volcanoes off in the back. It's probably volcanically active, as is the Earth, but it's a completely different style of geologic process relative to the Earth. Next. So gosh, the Soviets actually landed on Venus with robotic spacecraft, and we're looking at one of the Venera landers, and we're looking at the surface taken by their imaging system, not off in the horizon. You know, we just kind of pasted in what we think the atmosphere would look like. But remember, folks, this is 800 some Fahrenheit in temperature. And what you can see is that kind of structure on the left, that's where they did a mechanical properties experiment where they just used a spring and whacked the surface and determined that it's rock. And you can see the camera lens cover after deployment. Interestingly, these spacecraft only last for about an hour or two. And the reason is, you know, they're battery powered and the batteries produce heat to power up the instruments, but the heat has no place to go because the outside environment is actually warmer than the inside. So the instruments and the spacecraft basically bake themselves to death. So you can't really be on the surface very long and survive. Next. So what to do to explore this really interesting sister planet? Maybe sometime in the 2020s, we'll have a balloon, and the balloon will lose some of the buoyancy, let out some gas, and then an instrument will touch the surface, gather some samples, and then go back upstairs where it's cooler. Because same as Earth, the higher up in the atmosphere you go, the cooler it becomes. But it's going to be very difficult to explore this planet. But gosh, it's a sister of the Earth. Why does it rotate backwards? Why does it have no magnetic field? What produced this runaway greenhouse effect with all the carbon dioxide? And interestingly, folks, the amount of carbon dioxide in the atmosphere of Venus is equivalent to all the limestones and the containing the CO2, carbon rather, as calcium carbonate. So it's like you take all the limestone on the Earth, decompose it, put the CO2 back into the atmosphere, it would be Venus-like. That's never going to happen. But why did all the CO2 stay in the atmosphere? Why didn't Venus have oceans? Why didn't the CO2 kind of dissolve and make limestones as it did on the Earth? So a huge planet, very similar to Earth in size and mass, but a completely different evolutionary path. That's comparative planetology, where you're comparing one planet to another. And next, please. Here we are on Mars, the red planet. The red planet, it's red. This is real color. We didn't make this up just to colorize the radar data for Venus. This is due to rust, iron oxides, in that it's, in the past, there's been a lot of oxidation and a lot of turning kind of other rocks into rusty looking rocks. Not always. So that dark area that you see is just filled with basically what's called a basalt, kind of like you have in Hawaii. And it's a really, really dark material. So today, no water, only ice today, except maybe for some salty brines, kind of like, you know, putting ice on your sidewalk or your driveway or your street, and then putting salt on there lowers the temperature for melting, and you turn the ice into water. Sometimes there may be salty brines beneath the surface, and sometimes coming up onto the surface recently. But generally, we're going to convince you, I think, that Mars was warm and wet early in geologic time, based on the RAC record. And for some reason, it went into the deep freeze about 3 billion years ago. Next, please. So, folks, we have cars on Mars. Sojourner was a little test vehicle that landed with Pathfinder in 1997. Spirit and Opportunity, identical rovers, robotic, no people involved. This is testing in the what's called the Mars Yard at the Jet Propulsion Laboratory in Pasadena, California. I was the deputy principal investigator for Spirit and Opportunity. They landed in 2004. They were supposed to last a few months. Opportunity actually lasted until 2018, was going well, except a huge dust storm came up, and these are solar powered, and it just lost its energy and we couldn't wake it up afterward. So on the right, there's the one I'm going to talk about. That's Curiosity. That's the one that's operating on Mars today. It landed in 2012. It's the size of a small automobile. And these are all robotic, and we'll talk about, you know, some of the results from Curiosity, which to me are really, really amazing. And Perseverance is the NASA rover that's on its way. It lands in February. And at the end of this presentation, I'll talk about the other spacecraft from China and from China and one other place that I forget. China. Oh, United Arab Emirates. The United Arab Emirates has a spacecraft called Hope on the way to Mars. The reason I didn't remember it is they usually don't launch vehicles. So NASA has one, the Chinese Space Agency has one, the United Arab Emirates Space Agency has another vehicle on the way to Mars. Next, please. Here's what you want to do. You want to make sure that you build your vehicles, you test them, you rebuild, and you spend what you need to make sure it's going to work. So you don't want to do what James is going to show you right now as he pushes the button in the middle of the screen. This is the arm simulated on the Spirit and Opportunity rovers. And that's a grinder for rocks that we developed and worked perfectly on Mars. There it goes. You don't want this to happen. This did not happen on Mars. This did not happen on Mars because we built the vehicles and tested them, rebuilt parts, made sure it was the best possible technology at the time, everything put together properly, and they both worked splendidly. And we're far out of warranty once they stop working. Next, please. Before we go to Curiosity, I want to talk a little bit about a relatively inexpensive NASA mission called the Phoenix Mars Lander. So the orbital data at the time from NASA and from the Europeans said, hey, we think there's water ice very close to the surface. And it might be super close to the surface, like maybe an inch down up above the northern Arctic Circle. And Mars has about the same spin axis tilt, same seasons as the Earth, although it's super cold. So we actually proposed and flew a mission called Phoenix. It was called Phoenix because we bought a used spacecraft, a used lander, and it all worked. And this was under the mantra called follow the water. And it was a test of whether or not the orbiter data from the different remote sensing systems actually were sensing water ice close to the surface. Next, please. So I co-led the search for a safe landing site and was the robotic arm co-I and led some of the operational planning. This was a descent on retro rockets after coming into the atmosphere at miles per second, using an aero shield to slow down, and then using a hypersonic parachute. And finally, the last leg was with these blasters, slowing down to come down at about a yard per second or so, and worked perfectly. Touchdown in 2008, just at the ending part of the northern spring into the summer. It lasted until November 2008, and it was so far north that after that, in the fall and the winter of the northern hemisphere, it got buried by 2 yards of dry ice, carbon dioxide ice. Because Mars is unusual, its very, very thin CO2 or carbon dioxide atmosphere actually becomes snow at the poles. So we didn't expect it to last beyond November of 2008 our time, because that got into the precipitation as CO2 frost and snow. Next. So where did we land? We landed in a place called Heimdall, close to Heimdall crater. So here's the interesting story. I was more or less in charge of naming things. So the best place to land, it turned out to be in the ejecta deposit off to the side of this 6-mile wide impact crater. This is due to some ancient asteroid or comet just being unlucky and whacking into Mars and digging a big hole. So what do we name these things? Well, we're in the north. Most of my relatives are from the southwest coast of Sweden, thus the name Arvidson. I said, hey, I think I'll name this after one of the gods, one of the Viking gods. So you look them up, and most of them were not very nice in terms of cutting people's heads off and doing other egregious things. Heimdall was not bad. He guarded the bridge between us and Asgard and did mainly that. So I went ahead and just said, we'll call this Heimdall crater. Immediately got a call from the head of the International Astronomical Union Naming Committee, who said, Arvidson, you cannot just name things willy-nilly. We have to do that. And anything that's about 6 miles in diameter has to be named after a small town. So, gosh, looked up. There is a town called Heimdall in Norway, convinced them to leave it, and that's how it became that name. You can also see in the lower left a parachute and a little white blob. That is an actual image from the Mars Reconnaissance Orbiter camera called HiRISE of Phoenix lander descending, not into the crater. It's kind of a weird perspective, but it actually went off to the side. And that to me is an amazing picture. So we landed on the ejecta deposits of Heimdall. Next. That's a view, kind of an artist's view of the lander. Not very big. It's about, comes up to about my waist in terms of the deck. So it had a camera, had a meteorology boom, had a laser to look up and look for reflections. My part, once we landed, was the soil probe with a scooper, and it had a little rasp to kind of grind into the ice, and then return that material back into the lander to test for the presence of water ice and a few other things. Next. So we're supposed to name things after fairy tales. And the principal investigator was Peter Smith from the University of Arizona. He said, Ray, Arvidson, people like fairy tales, so we'll resonate with that. Let's name everything after fairy tales. So that's one of the first pictures with the solar panels deployed, and you're looking at the deck, and then the camera looking off to the side. It's a kind of a boring landscape. It's broken up into polygons produced by ice. And there's Jack's house, one of the few features off on the horizon. So we named it Jack's house, and you can see the reference to a fairy tale story. But didn't all go well. Next one. When we deployed the robotic arm, there's a camera on it, and we could look underneath. And that's underneath where it says, holy cow. that is where the retro rockets coming down actually blew away all the soil, all the regolith, and exposed pure water ice. So it's one of the first pictures from underneath the lander. So when I came in for operations that day and was running the show, I said, holy, I didn't say cow, I said a bad word that begins with an S and ends with a T and is one syllable. So we decided we couldn't use that. It was an amazing discovery. So that's how it became holy cow. It's the only thing that I know of that's not named after fairy tales. Next. Okay, so you saw the boom above the deck, and we really couldn't afford a formal instrument to measure wind velocity and direction. So we had a Danish team, and the Danish team got this little brace. This is right above the deck. And you can see that on the left-hand side, that little weight blowing back and forth. That's the actual Mars wind blowing that little weight. And we calibrated it before we landed. And at the top, at the edge of that little arc there, you can see something that looks like a cross. That's projected by sunlight down onto that plate. So we measure the direction of the wind based on where it's going relative to those four coordinates. Looks like a cross. And then we also measure the magnitude based on how far beyond the center of that cross the weight goes. It actually worked, and we calibrated it on Earth beforehand. On the right-hand side, it's the same boom, but the wind's not blowing very fast. But you can see on that little plate with the cross, little white dots, that's actually water ice snow coming down toward the middle to the end of the summer. So it actually snows on Mars, water ice, a little bit, in addition to a massive amount of carbon dioxide ice when it gets a little colder in the winter. So that was follow the water, and we found it in form of water ice. And we found water ice that were cubes broken up, and you could actually use them to put into your soda as ice cubes. And we also found pore ice. So follow the water, been there, done that. And if you see another piece in a paper that says we found water on Mars, it's old news, 10 to 15 years old. We're on to something else. And let's get the next slide, please. And that is, going from follow the water, we know it was there. Was Mars once habitable? Was that ice once water on the surface, sustained on the surface, and in the subsurface? And the answer is definitely yes. And then we want to move from that to, did Mars produce and preserve organics, and then eventually a direct search for life? We're not there yet. So I'm going to tell you that Mars was habitable in the past. It had lakes, it had rivers, and that it preserved organic molecules. Although we're not sure if they've come from outer space in meteorites, if they were made biologically, or they were made geologically. But let's take a look at the evidence for habitability. Next, please. This is not Mars. This is Death Valley. And we're looking off at the Panamint Mountains on the western side of Death Valley. The reason I show you this is Mars was really active with water in the past, but then it became basically cold and dry. And I'll talk about why toward the end of this presentation. But while it was warm and wet, it produced what are called alluvial fans. It had shallow lakes or ephemeral lakes, so that you can, it's red at the top of the Panamint Mountains in California because this is false color. It's not what you'd see with your eyes. It's increased in wavelength out to a little bit to the infrared. And in the infrared, vegetation, in this case, a whole forest growing at the top of the Panamints is red. And then coming down the side, you can see the mountains carved, and then this massive amount of kind of fan-shaped debris. So what happens is the snow melt and the rain in the mountains erodes the rocks, and then it dumps out as these fans, and then it goes all the way to the base and intersects this flat kind of ephemeral lake or playa that in fact forms Death Valley. And then the red at the bottom, the intersection of the fans and the lakes, that's where there's a lot of springs coming up. So you have these marginal kind of swampy environments. And the white in the lakes is all salt from evaporation. So that's Death Valley. That's not the Earth. But take a look at the next slide. So we landed with Curiosity, and I'm on the science team to help with traverse planning and strategies. and also some of the science, we landed in a 96-mile-wide impact crater, ancient crater, billions of years old, and landed close to this central mound, about 3 miles high, called Mount Sharp. And it's all layered. Those rocks in the mound are layered. They're sedimentary rocks formed in surface processes, by surface processes. So what we're doing is driving up the side of that mountain. And as you go upstairs, further and further, you're going from older rocks at the bottom to younger rocks at the top. So it's like a strip chart recorder of the geologic and environmental history of the planet. Mainly, we've explored the bottom. And in a couple, 3 months, we're going to kind of move up to a much steeper set of rocks. Should be really interesting because it will reflect, I think, a drying out of the planet and what kind of happened to go from warm, wet to dry and cold. And next slide, please. This is a top-down view. It's a little difficult to explain. On the lower right is Mount Sharp. The upper left is the edge of the crater called Gale. And see where it says Peace Vallis? That's a big channel that carved right through the ridge, the edge of Gale Crater. And you can see where it says Peace Vallis fan. It's just like the Death Valley fans. It's sediment that's come out long time ago, billions of years ago, brought in through the river Peace Vallis, and then dumped out where the slope became a little less. Then as you go down toward the middle bottom of the screen, Bradbury Landing, named after Ray Bradbury, is where we landed. And then where we've been driving since then is shown by white. And I'll show you the Bradbury Landing site from the Curiosity cameras, and then go to point A to show you what the rocks look like. Next, please. Excuse me. So this was a big vehicle. It's a metric ton. It's the size of an automobile. The wheels are about 1 yard high. So airbags were not a possibility that we used for Spirit and Opportunity, nor were, for that matter, retro rockets. So NASA and the Jet Propulsion Laboratory developed this sky crane, and the rover was carried underneath it, and the sky crane with the retro rockets. This is after an aero shield and parachutes, and the last part was a sky crane with the rocket blast as shown. So maybe 30 yards above the surface, and the vehicle of interest, our rover, Curiosity, was let down on cables. The cables were cut automatically. The sky crane moved over and then settled down somewhere else. So we landed wheels first. And where it says landing site, that's exactly where we touched down. But the cool thing is the retro rockets blew away the soil and the regolith, just like the retro rockets did on Phoenix to produce the ice. But here we're close to the equator. We didn't expect any ice to be stable. But it did the next best thing. And on the next slide. That's one of the areas that was blasted out by the sky crane. Guys, these are ancient conglomerate deposits. Any of you who've had freshman geology will recognize that this is a sedimentary deposit. And in fact, it's an ancient gravel bar, probably in an ancient alluvial fan. Must have been transported and deposited by water, because you see kind of a mixed set of sizes, some rounded, some not. It's exactly what you'd find on the Earth in a river bar, as shown on the next slide. Well, there are two ways to demonstrate that this is not Mars. One is the people, and then secondly, the mountains are a little bit too ominous and high. But this is an old gravel bar in an ancient stream, actually a modern stream in Chile. So it's exactly the kind of material, cementation, distribution of pebbles, very poorly sorted, that we have for the area blown out by the retro rockets. Next time. Next slide. Well, the robotic arm on Curiosity is huge. It's about twice the length of my arm, and I'm a 6-footer, so that's pretty long. And the end has a number of instruments, including a drill that I'll talk about in a minute, but also a beautiful camera called Molly. So we can actually move the arm around and take selfies. So this is an actual picture of the vehicle on Mars back a few years ago when it was sitting on a little bench. And that bench, when we looked at it closely, is made out of river sandstones. Right beneath it, those are lake beds, they're mudstones. And the vehicle, as of today, has traveled, or tomorrow, has traveled 14.3 miles. Our rover Opportunity has the world's record, far beyond a marathon. But Curiosity is on its way. Curiosity, by the way, is not powered by solar, but rather by plutonium that's hanging off the rear end that provides heat when it decays, and we charge up the batteries through a heat exchanger. Next. So let's take a look. Now, as you're moving along, we landed in 2012 and been driving and measuring ever since. You have to name things, otherwise you lose track of what's going on. So for example, Pahrump is a town in Nevada. So we did a lot of work at Pahrump Hills, and that white line represents the traverse of the rover based on safety, avoiding the hills, avoiding big rocks and sand pits, and also science. So the Pahrump Hills, and the next slide you're going to see when we get to it, boy, this is eerily like the Earth in its desert areas. And the reason is, it was produced in a warm, wet environment, and then wind has stripped it since the planet went cold and dry. Next. So it's always exciting to come into the office, after a drive and to see the new landscape that no one ever has seen before. And it's so Earth-like, except no vegetation on the surface. So Mount Sharp is up to the upper left. We drilled into these what are turned out to be lake beds in the Confidence Hills area. I'm going to show you blow-ups of Whale Rock and Salisbury Peak. Next. And that's A. And that rock is, maybe a meter across or a yard across. And you can see it has tilted, very thin beds. That's a dead ringer for a sandbar in a river. So the whole mantra, the whole set of data we're collecting argues out that we had an ancient river system that, based on all the impact craters that we see superimposed on this area, probably was active last maybe 3.3 billion years ago and then stopped. Next. And then this is the other view. And the bottom you can see coarse grained rocks, those are conglomerates, and it binds upward stratigraphically. You can see those layered rocks, kind of the bluish ones above the words conglomerate end. So this is basically, we think, a channel system that's carved into the surrounding lake beds and just produced these river deposits that got finer and finer as the energy decreased billions of years ago. Warm, wet conditions, sustained water on the surface. Not today. Next. Mud cracks. As we continue to drive, you're looking, folks, at maybe a 3.3 to 3.5 billion year old surface of a lake that dried out, that was buried by other rocks, and then by wind erosion is being exposed. To me, that's totally spooky. So if we were standing there maybe 3.5 billion years ago, we'd be standing on a shallow lake that was drying out, and the mud was undergoing desiccation or drying and cracking. And in other places, we see evidence for fractures or joints through the rocks filled with calcium sulfate, which means that groundwater was percolating through probably long after the surface water was evaporated or froze over. Warm, wet conditions on the surface and in the subsurface for an extended period of time. And next, please. So here's the environment. We had river deposits coming in from the edge of Gale Crater. They met the lake to form delta, like the Mississippi Delta, but much smaller. And then further out into the lake, that's where the fine mud accumulated and deposited. So that was we think the kind of artist view of what was going on billions of years ago, because we started with Peace Vallis from the orbital picture, and we saw the fluvial deposits. We saw evidence for fans. The delta I didn't talk about too much, but it's all there, and you have to really go into the details of the distribution of sediments and how they're geometrically aligned and the presence of cross-bedding, etc. But you saw the mud cracks. Those are ancient lake beds. Next. We also drilled, and those holes are about the size of your pinky. And the mini drill was a test, and the full drill actually got the rock powder. And you can see once you take away the rust, it's really kind of a gray rock, not all that kind of weathered and corroded. And the instruments on board, one does the minerals present, the other looks for organic materials in addition to other materials, take about aspirin size chunks of that very fine powder to do their work. So it's amazing that we can use that huge robotic arm, we can drill, we can get that powder, get it back into the rover and do very detailed analyses. And we find organic materials. And they're probably, for those of you who are somewhat chemists, they're probably materials that started out as kerogens, that is organic compounds that were very kind of refractory and then have been broken up. And they're variously aligned with sulfur and with chlorine. So they're not pristine, but the fact that they're preserved is amazing. And we don't know if they're biological in nature or if they're brought in by meteorites. And carbonaceous chondrites have a lot of organics, and Mars has a lot of meteorites falling on the surface. Or they could be produced by some geologic process that we need to kind of work through. So we can't tell if it's evidence for life or not. But the really neat thing is they're preserved in an environment that was warm and wet with water sustained on the surface and subsurface water percolating through for what was probably a long period of time, even after the surface water was gone. Next. So that's kind of a view of habitable Lake Gale several billion years ago. And here's the weird thing. Mars on average is 1.5 times further from the Earth, from the sun than the Earth is. So it gets a lot less sunlight. And it was warm and wet when the sun was just catching fire, just having its nuclear furnace going on. So it was less strong than today. So what's going on here? Mars is further away from the Earth and the sun was less strong. And that's when Mars had its heyday. So what was happening is, when Mars was first formed, it was super hot, as was the Earth, because planets form by smaller planetesimals kind of coming together at high velocity, producing heat. And that heat produces melt on the inside. Then the core forms, iron-nickel core. And when that forms, it's more heat. Plus there's radioactive decay from uranium and thorium and potassium. And that all was really generating a lot of heat early, a lot of volcanoes, which we see on the surface. And that produced massive greenhouse effects to get this planet up to warm, wet conditions. But Mars is smaller, it's half the size of the Earth. So it kind of cooled down more quickly because as a small planet, has a lot of surface area relative to its mass. And it kind of conked out, you know, without a lot of volcanism, the greenhouse gases were lost to space or turned into rocks. And today you have this very, very thin atmosphere of carbon dioxide and a few other things, but maybe 1/100th as much as the Earth has. So the greenhouse effect is nil. So it had its heyday early, whereas Earth is still going and will be going for a long period of time. And who the heck knows what the history of Venus is, you know, with its runaway greenhouse effect. But those 3 planets are really interesting to study because they tell you a lot more about the Earth than studying the Earth only. Next, please. So this is the view out of the front windshield, if we had a windshield, of Curiosity. We're actually right about at the end of that dashed line. And we're climbing those rocks. And the further up we go, you know, the younger the rocks. The rocks that we're on right now were produced in this river kind of delta lake environment. The rocks we should climb onto probably early 2021, I think are going to represent a lot of salts, a lot of drying out, sulfates and other materials. And the youngest rocks we think are totally windblown. So as we drive upstairs, you know, we'll still look for organics, but what we're trying to do is interpret the change in the environment of this red planet as a function of time, and a little bit more in terms of habitability when it was present, and what happened, you know, as you go through this warm, wet set of conditions to cold, dry conditions that we have today, and what happened in between. Next, please. So, habitability and life scoreboard. Sustained presence of water, you got it. early in geologic time, on the surface, in the subsurface, as liquid water, circulating, hydrologic cycle for sure. Biochemically crucial elements, yeah, they were there. Not sure if they went beyond kerogen or we had the appropriate bioavailable compounds. Energy sources, sure. There's the sunlight. Microbes on Earth actually eat rock, so there were a lot of rocks on Mars. And of course, heterotrophs eat other life like us, so that may also have been a pathway. Protected environments, sure enough. We know Mars had a magnetic field early before the core froze, and it went into the deep freeze, and a denser atmosphere. So the earlier you look, the better it looks in terms of habitability. We haven't the foggiest, we have no way to tell if Mars actually developed life and it evolved, and is it even there today? So that comes up in the future, in the next several decades, to try to kind of put this question to bed. Next, please. And gosh, Mars is a popular place. And this is a bit of an old slide. You can see on the x-axis is time. There is no y-axis, it's just showing the various spacecraft. A lot of orbiters from the European Space Agency, from the Indian Space Agency. There is a Chinese orbiter on the way. There's a United Arab Emirates mission on the way. We have the Opportunity and Spirit rovers. We have the Curiosity rover still going. European Space Agency in cahoots with the Russian Space Agency was to launch a rover called ExoMars this year, but COVID basically put them 2 years back. We have InSight on the surface of Mars since November, and it's detected Marsquakes. That's a NASA mission. The Mars 2020 rover now has a name, Perseverance. That's on the way. It lands in February. The Chinese have a rover on its way on the top of a lander. And as we talked about, the United Arab Emirates have Hope. The 2020 rover, or Perseverance, is basically Curiosity with a new set of instruments. And it will land in a place called Jezero Crater, which has a delta. And it will land, and the arm will have a drill, and the drill will get rock cores. And those rock cores will be encapsulated in a biologically protected encasement. And sometime in the 2020s, another robotic mission will go and get them. And we've been trying to do a Mars sample return for a long time in a location that would maximize the chance of answering the question about organics and life. And getting those samples back, boy, that's a mission that keeps on giving and giving and giving, because you can do a whole lot more in a laboratory than you can on a rover. Plus, the instruments get better and better with time. So we'll be looking for biosignatures, looking for direct evidence of microbial life in terms of fossils and everything else you can do. Plus, folks, you can see SpaceX Dragon. One of the reasons Elon Musk put together Tesla is to make money together with his ability to send astronauts now to the International Space Station and cargo, is to get ready to explore Mars with humans. And the SpaceX Dragon might land robotically in the next few years with an intent of putting people on Mars, for better or worse, sometime in the next 20 to 30 years. Why are we doing this? Let's go to the last slide. This is not particularly exciting in terms of an image, but it means a lot to me. That little dot is the Earth. And this was taken by the Spirit rover with its PanCam during sunrise with the Earth present in the background. We're doing all this to better understand ourselves. You know, where did life begin? Is it unique to the Earth? Does it have other locations in our solar system and beyond? To look at Venus, look at the Earth, look at Mars. Gosh, they're different. And yet they're roughly in the same part of the distance from the sun. It's only today that we think that the Earth is in the Goldilocks zone or habitable zone. Mars was in the past. Gosh, what happened to Venus, to make this bizarre climate on the surface and metal rather than a hydrologic cycle per se? So we're doing this to better understand ourselves. And it all plays back in terms of understanding each planet, including the Earth. The other really interesting thing is we know there are meteorites from Mars. because you can pick them up, bring them back to the lab, you bake them, they smell like Mars. You can't smell them. You bake them, and the gases that are given off have compositions and what are called isotopes of the atmosphere of Mars, which is unique in terms of patterns, nitrogen 15 to 14, for example. And I'd be happy to go into that with questions to the extent that's possible. So Mars and the Earth were exchanging meteorites. Suppose that microbes living in a big chunk of Mars got blasted off and landed on the Earth. Guys, do we have Martian ancestry? I think some of my students do, based on the way they act, but who knows if that's the case or not. So that's my pitch. Mars was warm and wet early in solar system history. It was certainly habitable, and we're on the search to see if, in fact, it had life at one time in the past. And studying on the planets tells you a lot more than any one planet and studying it itself alone. Thank you very much, and we can go to questions. And I can see we have a number of them. Okay, let me start with Dennis from Largo in the US. Why is our search for signs of life anywhere in the solar system always focused on microbial? Well, we've done a lot of imaging on Mars, for example, at a number of scales, including 2 landers, the Viking landers 1 and 2 back in 1976, Pathfinder in 97, Spirit and Opportunity in 2004 through a few more years, Phoenix, and then Curiosity. There's nothing that's suggested in any part of the planet for life beyond microbial. So we're looking at, basically the most primitive form of life that you can imagine, beyond virus into microbial. And the other point is Mars was never, never, never as wet as the Earth. It never had full oceans. So we're looking probably for pockets of life, and it doesn't have the conductivity, this explosion of life that Earth has. So we think that most likely it got as far as microbial. And likewise for the outer planet satellites, the icy moons, we're thinking probably it's at microbial, which is the most widespread, perhaps the most abundant life on Earth anyway. And let's see, Alan from Myrtle Beach. Would there be enhanced observations and research by physically being on the planet of Mars? Yeah, that's a good question. Why should we send people to Mars? I don't think science drives it, because by the time we're ready to send people to Mars, the development in robotics will be so advanced, they could do probably much of what folks could do on the surface. But if we find evidence for ancient life and an environment that was hospitable, certainly for an extended period of time, I think, we're explorers and we'll have people there at some point in the future. Colonization and, the whole concept of colonization and terraforming is, in my opinion, kind of goofy and not really realistic, at least for the next century or so. But scientific exploration, kind of like using Antarctica, certainly. Also, there are probably no huge piles of ores on the planet, because Mars just didn't evolve as much as the Earth has geologically to produce those ore deposits that we depend on for our economy, or oil deposits for that matter. Let's see, isn't Mars closest to us right now? Yeah, it is. Mars will only be 39 million miles away from us on October 13th. It's in opposition, and that is on the opposite side of the Earth relative to the sun. So as I said at the beginning, if you're outside in the United States or the Northern Hemisphere, just after sunset, it's that reddish dot on the eastern side of the sky. And if you're an early riser like me, during the like 5 in the morning or so, you can see Orion, you can see Mars kind of setting off to the west, and you can see Venus coming up on the east. So it's pretty exciting. And you can tell Mars because it's red. It's rusted. It's rusted from back in the day when it was warm and wet, most likely. How much did Curiosity cost to build and send it to Mars? And by the way, the last question was from Roger from the US. Tracy from Kansas City said, how much did Curiosity cost to build and send to Mars? To get it to Mars, $2.65 billion. Perseverance is a little bit cheaper because we've already built one vehicle, and building Perseverance is some money savings. Now, where'd that money go? It went to salaries. It went to technology development. So it's not like we took a big pile of dollar bills and put them in a bonfire. It's an investment in our economy. And it's what we do. We explore, we try to find out who we are, what our solar system is about. But $2.65 billion. And as I said at the beginning, you can't do this on the cheap because it's a really, really, really harsh environment. So you have to have vehicles that can withstand huge changes in temperature over time and that are able to trek across rather diverse surfaces. And Wilford from San Francisco says, let me see here, how many on a team are involved in creating the rovers you were involved in? We have a science team of 400 some folks from the United States and from Europe. And one of the instruments is actually Russian, from the Russian Space Agency. So it's international in scope. Spain provided the meteorology experiment. So it's certainly, international in scope. The number of people involved in building, designing, building, launching Curiosity is probably 1,000 or so, because it started, actually I wrote the original science definition report for NASA back in the year 2000 for this. And it was started to be funded a few years later, not launched to 2012. So it is a big deal to put together. And again, you're paying people salaries. So it's an investment in our economy. And it's international, so it's international cooperation. And that's Wilford from San Francisco. Fanny from Cambridge said, do you ever think of becoming an astronaut to get closer to what you are so passionate about? I kind of like my job. I kind of like coming in the morning and being one of the few human beings on Earth that can see these alien landscapes. And I get so excited with my students. And I also love teaching, as you might imagine. So I had no yen to be an astronaut. I was in the Air Force, and that got as close to the space as I desired. So I look at it, I'm going to space every day. We're going to Mars every day, kind of virtually. And Demario from Ellisville. What is landing a rover on Mars like? How stressful is it? Oh my gosh. Okay, so here's how you get to Mars. You have to launch, and we launch from Cape Canaveral in Florida. And then you have to jettison the rockets, and you have the vehicle encapsulated in its transport spacecraft, and you have a kick stage. So you orbit about Earth, and then you kick out of Earth with a thrust from the rocket, and then you jettison that rocket, and there are other rockets still on there. And then you're in orbit about the sun. It's called a home and transfer orbit, and it's about a 6-month journey, and you have to do it in such a way that you get to Mars when Mars is there. Otherwise, it would be totally embarrassing, and the project manager would have to report back to the head of NASA and Congress. So now, for Curiosity, we did what's called a direct entry. You're able to adjust the orbit a little bit so you get within maybe 20 miles or so of where you want to go, which is amazing with the NASA JPL engineers. And then you enter the atmosphere at miles per second because you're in space. So you use an aero shield to take a lot of that energy out. And then you use a hypersonic parachute. And with Curiosity, it's so big, it's a metric ton, that we had to use the sky crane with the rocket patterns coming down, and then letting the rover wheels down on cables, cut the cables, and then the sky crane goes off and lands somewhere else. And then you're ready to go after instrument checkout and mobility checkout. The scary part, the really scary part, is we don't exactly know the characteristics of the atmosphere because it has a lot of dust in it. The Mars winds are actually blowing dust. And if there's a lot of dust, the atmosphere kind of swells up because the dust absorbs the radiation from the sun. So you can't tell exactly what the entry profile is going to look like. And it's all done automatically because entry from the top of the atmosphere to on the surface is like 9 to 12 minutes. And it takes longer than that for a radio beam to get back to the Earth. So when this happened back in August 2012, the science team was there, the engineers were there, And that 9 minutes was just one of the scariest things. So it's 9 minutes to happen and another 15 minutes or so for the signal to get back. And as you might expect, after working on this mission for many years, there was massive applause, and I hugged people I'd never met before. So getting it down on the surface is really, really difficult. Not many vehicles have made it. Most of the US vehicles have made it. The Russians have not. The Europeans tried to land basically a sledge, and it never slowed down. So, and the European Space Agency, the UK Beagle, likewise didn't land successfully. So it's pretty scary. And again, it gets back to what I said, you get what you pay for. You test, you build and rebuild until you're doing the best possible job in terms of having a high probability of landing successfully. But it's worth it. And Tressa from Austin, Texas. Oh, Avenue 5, the HBO series. I watched every episode, some of them a couple times. It's hilarious. And since this is Viking.TV, Avenue 5 is taking basically a ship like a Viking ship, like the Jupiter or Orion, putting it in orbit, and you have a captain, you have a cruise director, you have cooks, you have assistants, you have the crazy kind of passengers. Viking has no crazy passengers, by the way, and it's a comedy, and hopefully it's back for the next season. It's hilarious and worth watching if you have HBO. Yeah. Ken from Alexandria. How did you get into this industry? What was your first stepping stone? How do I go about it? I go back to Sputnik, and I was in New Jersey, and as we did Sputnik and then Explorer with the US, you know, I just remember cutting out of the paper and putting it in a scrapbook and saying, hey, this is so cool. And then grew up during the Apollo era, and I was either going to go into oceanography or planetary sciences, and planetary sciences got my interest the most. So I wound up getting a PhD in planetary sciences, and then was in the Air Force for a while. And then came to Washington University in St. Louis as a professor because of James S. McDonnell, who founded McDonnell Douglas and was a benefactor to our institution. So we have a number of space scientists and staff and postdoctoral research associates and graduate students doing a variety of space science work. So if you want to get into this, you know, what you should do is pay attention to what's going on. And there are also internships once you're in college within NASA and within various universities to kind of get a feel for doing some of the research. So, you know, follow your passion, and you'll get there. Don't give up. It took Steve Squires, who was a professor at Cornell at the time, and myself, 5 different proposals to get Spirit and Opportunity through the proposal mill to get them approved and launched. And that took many years. And let's see. Quentin from Atlanta, given these new water developments on the red planet, do you think it's feasible to start seeing more signs of life in our lifetime? That's the whole idea. You know, the hope, the orbiter for the United Arab Emirates is basically look at the atmosphere. The Chinese orbiter will be looking at the surface in the atmosphere. Their rover is looking at another part of Mars that we haven't been to, you know, searching for signs of habitability. Perseverance is exactly designed for answering the questions that you posed, and that is getting samples back in addition to making in situ measurements that are related to biosignatures. And then the European Space Agency, Russian Space Agency, ExoMars will launch in 2 years, again designed to look at habitability. It's all focused in on whether or not this warm, wet, early planet had life. So I think we'll answer it within some number of years. Maybe not before my retirement. I think that's it, folks, unless there's another question. This was a lot of fun. I hope some of you on board this session actually traveled with me on Orion or Jupiter when I was the resident astronomer, or an enrichment lecture on the sky or the sun. And if not, you know, please come on board in the future. Viking is just a blast. It's a well-run organization, It is #1 rank in enrichment lectures, not because of me, but because of the overall enterprise. So thank you very much for your patience and the wonderful questions. And let's get on and try to figure out who we are. Thank you very much.